The most important device, one of the most important devices for our grid is the transformer. If you remember earlier, we talked about the fact that we want to boost the voltage of our electricity to a high level such that we can deliver a lot of power and not have a lot of current. The power loss on an electric line goes by I squared times R. So if we can boost our voltage and lower our current, we can send a lot of power over the grid, but at a very low power loss. Of course, when we boost this voltage to 500,000 volts, we need to bring it down to a safe level before it can get to our homes. And that, of course, is where the transformer is going to come into play. So we're going to see two different types of transformers. We're going to see a transformer which is basically a step-up transformer and boost the voltage so we can send it a long distance. And then we're going to see a step-down transformer to drop it to a voltage level where it is usable by the consumer, by the resident. So let's start by, of course, looking at how the transformer works. It basically works by saying we have a voltage source on one side. We'll call this the primary. And this creates a magnetic flux, which is then concentrated by some type of metal core. This is then picked up by a secondary loop. And through this mutual inductance, we are going to get a different voltage here compared to here, because essentially the number of coils I have here is going to determine the voltage on each side. So for instance, we have 1, 2, 3 windings here on my primary input. If I have 4 here, I will have 4 divided by 3, 4/3, okay, 33% higher voltage over here than I have over here. Now that comes at a cost of current. So if this is an ideal transformer, much like a machine, you can only have so much work input. You get an equal amount or less output. Here, the power coming in is going to have to be at least kept to the same level or dropped a little bit due to resistive losses over here. So boosting the voltage, I can't get energy out of nothing. I have to reduce the current, so the power on this side is going to be equal to the power on this side. Okay, so again, on this side, we have the primary. On this side, we have the secondary. So the voltage divided by the number of turns is going to, on the secondary, is going to be equal to the voltage divided by the number of turns on the primary. Those two things have to be balanced, because that's really saying the magnetic flux over here is equal to the magnetic flux here. And thus the mutual inductance between the two is related by the number of coils on each side. So let's take a look at a step-up transformer versus a step-down transformer. These devices would be very useful if, for instance, you're traveling to Europe where their voltage is higher. Frequency is also a little bit different. So this is not, a perfect example, but you can actually get adapters that allow you to go from US current to European current, or from European to US. I should say voltage is really what we're happening here. So our step-up transformer would go from what we would have in the US, about 120 volts. By doubling the number of coils on the secondary, I could get a voltage that could be used by European appliances. When, if I travel from Europe to the United States, if I go from the United States to Europe, I would want a step-down transformer, dropping from 240 volts to 120 volts. So the step-up transformer here had twice as many coils on the secondary as the primary. Here it had twice as many on the primary as the secondary. And you get this idea that as we step up, the secondary coil is going to have more turns in it. Here it had 10 turns compared to 5 on the primary. And when we step down to get that drop in voltage, there are fewer on the secondary than there were on the primary. In this case, we had 10 on the primary and 5 on the secondary, meaning that my 240 volts or my 220 volts was converted to 110 volts. Now, again, if it's an ideal transformer, the power in is going to be equal to the power out. The power coming out of a transformer is going to be the power on the secondary loop times the voltage on the secondary loop. The power in is going to be the current on the primary loop times the voltage on the primary loop. Again, you can't get something for nothing here. So power out has to be equal to power in the best case scenario. Normally power out's a little bit less. So what that happens is you get a little bit of a voltage decrease than you would get for an ideal transformer. And again, for electrical transmission, this is very, very important because our power losses are equal to the current squared times the resistance. Our power delivered is going to be equal to the current that I send over the transmission lines times the voltage at the end user. So very, very important that we understand that typically we step up from the generating station to the transmission lines, and then in steps we'll step down. Now, the current wars was the oftentimes misrepresented battle between Edison's company, who was beginning to deliver commercial power to different users, and the Westinghouse company, which Nikola Tesla was a part of. Now, this is oftentimes presented as a battle between Edison and Tesla, and certainly Tesla was a big supporter of AC, but what it really ended up being is a battle between Westinghouse's company and Edison's company for the contract at Niagara Falls. And Westinghouse and Tesla were able to show that you need to boost the voltage to send it over a long distance to reduce these losses, which Edison was not willing to do with his system. Now, today's that's overly simplified, but today's grid is basically this system that Westinghouse and Tesla had developed. That again, you boost the voltage at step-up transformers at the generating station. This is sent over lines from anywhere from about 138 kilovolts all the way up to about a megavolt. That you would then step this down by substations, and instead of just a single station, there are actually many substations. As we deliver it to different regions. But over long distance, the farther you go, the higher the voltage you want, because you want to reduce your power losses as much as possible. So, for instance, if we think about how power might get to our houses. Let's say that at a power plant, the generators produce power at 15,000 volts, 60,000 amps. If I put that straight on my high tension lines, that would result in a huge loss of power. You think about the power that you would actually lose, you'd end up probably losing more power than you'd actually deliver. But if we can boost this to a much higher voltage, remember, we're going from a primary with fewer turns to a secondary with more turns. I could go from like 15,000 volts to 500,000 volts. I drop my current. And if my total delivery transmission lines had a resistance of about 1 ohm, that would result in only 16 megawatts of power loss, compared to about 1 gigawatt or 1,000 megawatts of power delivered. At the substation, of course, 500,000 volts is very dangerous to send over normal residential transmission lines. So this would be stepped down probably to about 24,000 volts initially, and then about 7,300 volts. This would be transmitted on the 300 volts would be delivered on the top lines on power poles. And then that could be converted from 7,300 to the 120, which goes into our homes. Again, overly simplified. You can have multiple transformers to step it up. Normally, there's a single transformer from a power station. Then you'd have multiple substations where you're going down in steps. Maybe you deliver it from a long distance to an urban region. Then there'd be a step down to smaller substation plants, and then finally, these pole transformers would step it down for residential users, or you might even have step-down transformers at industrial sites. So again, we start with electrical power at the source. Again, typically in the tens of kilovolts. It's then stepped up by these transformers, and you can see we've got sets of three. This is three-phase. The step up all three phases. And here are a set of three. Here's another set of three, probably going off in two different directions along these power lines. And again, once these power lines reach a substation, the substation will then step it down. And then finally, after it's stepped down, perhaps another time, we'd send it to one of these pole transformers, where in fact, you'd drop down to the 120 volts, which is a lot safer for your home. And again, two hot leads, probably at 120 each, so that when you look at the taps on some of these, this tap would be at 100 volts, this tap would be at 100 volts compared to this neutral. And then this compared to this, because they're 180 degrees out of phase, would give you a total voltage of 240. So here's a transformer that sits in the bottom of one of these. These are your high voltage taps coming in at 7.2 kilovolts. And then, our output connected to the secondary coils at 120 volts. And again, the whole setup, here you have at the top of the pole, normally the higher voltage, 7.2 kilovolts. Usually we're only taking a single phase here. Here's a fuse in case something goes wrong, we draw too much current for the transformer. This fuse will blow. And then again, we have our primary input. And of course, we also have to ground this. And then again, hot one, hot two, and then your neutral. Inside the transformer, there are actually two secondary coils. And the way it works is this. The full secondary coil between the top and the bottom here, this tap and this tap, is going to be 240 volts. But halfway through the coil, we connect this to 0 volts. And that'll give you a 120 between here and here, a 120 between here and here. And again, we've got about a 30-to-1 ratio between the 720 volts and the 240 volts as we're stepping down here. Now, one of the problems that we have with long distance power distribution, and this is becoming more and more of a problem as we get to green sources of energy, such as offshore wind farms, large photovoltaic, solar farms. We can produce power offshore very easily with wind farms where some areas don't have a lot of wind. We can produce solar, usually in the southwest of our country at very high quantities where sunlight's very prevalent. If I want to send that energy over long distance, sending it at 500,000 volts AC creates a problem because of the impedance of the delivery system, which means that what you have to do is you send it some distance, there's going to be a problem with the power factor as things get out of phase. You'll have to correct that and then send it on its way. It becomes very, very expensive. Um, Edison's idea of sending everything DC sort of has reemerged. And with the advent of large semiconductor devices known as thyristors, they're really the cousin to transistors. They're really a three-level transistor. These things are absolutely massive. Look at this person right here. These are the thyristors. Can be used to convert AC to DC. And now we can send it DC, not worry about impedance and power factor problems. We're able to send it a much longer distance. And then using inverters, we can convert the high voltage DC back to AC where it can be distributed on the grid again. So this is a change that's been happening where we convert AC to DC and send it a long distance and then convert it back. This is actually the same thing that happens with our phone chargers. Uh, when we plug our phone chargers in, we're plugging them into 120 volt AC. How do we drop that down to a usable voltage that can charge our phone, say down to 5 volts DC? Well, the way that it works is that we have to step it down, maybe from 120 to 5 volts. Um, we convert this from AC to DC using a, uh, a bridge of diodes, and then we smooth it out using a capacitor. So here's how it works. First of all, we have a step-down transformer, which is going to reduce our overall voltage. Again, we're not there yet. We still have AC, and that's not going to charge your battery. We need DC. So our USB then requires us to send it down these bridges, and a diode will only let the power flow in one direction. So we have this oscillating AC going back and forth, back and forth. When it's one polarity, we'll go down this bridge, okay? When it's another polarity, it'll go down the opposite bridge. And you can see that it always maintains the same polarity down here. So all you need are these 4 diodes. And again, here's positive, so it'll go down here. When we're at one phase, half a phase later, positive then makes it down this branch to connect to the positive here, and vice versa for the negative. So we take our AC, we sort of invert the negative troughs right here. We turn these upside down by sending it through this bridge right here. And then from here, this can be smoothed out, where if I hook it to a capacitor, the capacitor will charge when the voltage is highest, it'll discharge when the voltage is lowest. And that will basically smooth this to a nice line if I set this up very properly. And again, our load at the end, charging a battery, will basically just see a constant voltage. So that's really, really important in terms of our different systems here. Even a computer power supply basically works off of this principle right here. It's a little more complicated because many of the circuits in a power supply are much more susceptible to changes in voltage. But here you can see a typical voltage supply, power supply, which a computer would use. And different systems would use different voltages. Some might use 12 volts, some might use 5 volts. The USB standards today actually vary the voltage to take up for the fact that higher power demands might require higher voltages. But some of the circuits, like the old TTL, voltage, 3.3 volts. I think that's right. I'm not an electrical engineer, but different systems will require different voltages. And we can see the capacitors in the system to smooth out some of the fluctuations. We can see the diodes and, various other systems. Looking at the entire thing, this would probably be your transformer coming in, And, of course, that is step down to a usable voltage. So again, um, the transformer, very, very important. It doesn't work with DC. It only works with AC. It allows us to boost the voltage or drop the voltage. We want to boost the voltage if we want to send power over long distances. We want to drop the voltage if, in fact, we want to use it for other things, for home, where, 500,000 volts is not going to be a good thing coming into your home. 120 works much better there. Or for digital circuits, we wanted to drop it to a low enough voltage. And then we can use diodes and capacitors to turn AC into DC.